Good morning, everyone, and welcome to today's session of Autodesk Virtual Academy, brought to you by KETIV Technologies. I'm Nigel Labayek, contrary to popular belief, because my name's not on the screen, but I am joined with the person whose name is on the screen, and that's Brian Munkel-Punsek.
Hey guys, how's it going?
For those of you who are returning AVA subscribers, definitely thank you. And for those of you who are brand new to AVA or the AVA community, definitely welcome and hope you stay for the ride. So again, Brian, thanks for being here this morning, and sit tight for the next half hour or so, and let's get started.
Yeah, thanks, Nigel. So I like to start off the webinars with a purpose or a why we do things here at KETIV. I have two bullet points here. One is because technology is rapidly increasing now more than ever. And if you're not at the forefront of that, then you're falling behind. And that's what we want. That's why we do these webinars here, is to educate you guys and keep you guys one step ahead of those competitors. And number two, think of this as a time saver. All the time that us engineers here at KETIV spend on modeling and 3D printing, we crammed it all into this 30-minute session here for you guys. So then you guys don't have to do those tests by yourselves. And I have a couple goals here that we will go through today. The first one being, if you guys have ever used the thread modeling tool in Inventor, then you might be familiar with the Cool Orange add-in or the app on the Autodesk website. I'll show you guys how to get to that. We'll also be importing a McMaster-Carr component. If you guys aren't familiar with McMaster-Carr, it's a website that has thousands of different hardware that you can pull from. We will also be editing threads directly, and I'll also show you guys a way to access the Excel sheet Inventor references so you can put in your own custom thread sizes. There's also continuous threading, which is the terminology I chose for creating a thread that goes through two or more components, or two or more using Fusion term here, two or more solids. And I'll show you why that's important as well. And lastly, we'll talk about best practices for 3D printing threads, the way you orient your model in the 3D printing environment or the slicer, or how what print speed you want to print at. I'll go over all of that at the end of the webinar today. So once again, like Nigel said, if you guys have any questions, leave that in the comments section. Or if you have any comments, leave that in the comments section of the GoToWebinar. So let's go ahead and hop over here into Inventor, and let's try threading this hole here. So first off, to thread, you can't do that while we're in the assembly environment. So what we're going to do is hop on over to the part and open up the part there. And now we have access to the thread tool, which we can simply select a face. This red icon or the red cursor here is indicating that it needs to be satisfied. So I go ahead and click that face there, and now it's white, and it's giving me a preview of what that thread's going to look like. We'll go ahead and hop over here to the specifications tab, and now we can choose the thread type, and we'll go ahead and stick with the ANSI unified screw threads. We can choose the size. It defaulted to 1/8 of an inch or 0.125 for us because the size of the hole originally was that. But let's say I want to try doing a 3/8 of an inch. So we'll do a 0.375. And it automatically changed the designation to a 3/8 inch with 16 threads. You can toggle between those as well. As well as class, you can choose whether you want a 1B, 2B, or 3B class. 1B being a more loose fit thread, 2B being what 90% of the industry uses, and 3B being more a high tolerance thread. So if that's more critical for your field, then you know to choose that. And then you have the right or left hand threading options. So let's go ahead and hit OK and see what happens. So it looks like we get an error. If we go to the drop down here, this error is because of an inappropriate thread size. And that's because the original hole size was 0.125, but we chose 0.375. And unfortunately, it doesn't adjust the hole for us. So what we're going to have to do is go back in here and change that to, or we're going to actually go back to the hole itself and change the size of this hole to the 3/8 of an inch. Now I can go ahead and apply that thread to the correct specifications. Cool. So now we have our threaded hole, but notice it's actually just a illusion. It's a picture, but it looks a lot like there's actually threads in there. If I click on that and go sideways here, you can see that's really just a cylinder inside. And there's a good and bad to it. Let's start with the bad. The bad, you can't 3D print that and expect there to be threads. And that's why we have this webinar today. But the good is that this saves CAD data. So essentially, if you have 1,000 different threads in your model that are pictures like this, then it'll run fine. But if you have all modeled threads and you have 1,000 threads in your model, then it will probably slow down your machine. So I would recommend.
Not just a probably. That's certainly slow down your machine, right? Because each of those threads is going to consist of like X many faces and edges and so on and so forth, right? It's not going to grab all of that as one face. If you think about how a thread is actually, not manufactured per se, but how threads are like visualized, right?
Yeah.
That's not one continuous face per se, because of all of the curvatures and the edges and all that other stuff. So it's going to be super, super heavy is the term that we like to use around here. Is the file's going to be super heavy. It's going to start grabbing all of your RAM, and then you're going to complain that it takes too long. So I want to say 95% of cases, you actually just want to do this, but there's some cases where you actually need the threads.
Yeah, especially if you want it 3D printed, then you have to model in your own threads.
Exactly.
So to model in those threads, we're going to use the Cool Orange add-in, which is located here. And if you don't have this yet, you would go here to the web browser, and I'm going to go ahead and post this for you guys as well. But it's in the Autodesk App Store. You're going to need to sign in, and then you could download this for free. It has 5 stars, so it's a good rating. And it's also indicated by this orange circle with that white envelope in the middle. And you can also upload your files to threadmodeler.com as well, if you don't have Inventor on your computer. But what we're going to do is, I already have this download, but you guys can go ahead and download this as well. I'll post it into the chat room at the end. But then after you download it, you get the Cool Orange tab over here, and then we'll go ahead and choose the Thread Modeler tool.
Yeah, you might need to enable the add-in, so just keep that in mind too. It's like if you've downloaded it, installed it, and it hasn't started, working, you might need to enable that add-in.
So once you have that add-in ready to go ahead and select the thread that you want to convert to a 3D model. Hit OK, and that's it. We got it. We have a 3D modeled thread that when you 3D print, it'll actually look like this. Just keep in mind that it does come in as another solid in the middle. So if I hide the visibility, this is what we originally started off with. So you can do maybe a combined maneuver before you export that out to your 3D printer. So now let's check the tolerancing between this and, let's say, a screw, for example. So a screw, I'm going to go ahead and pull from McMaster-Carr. And if you guys remember earlier, I talked about how McMaster-Carr has thousands of different hardware, a lot of which have CAD files associated with it. And especially the ones, the screws and bolts, those especially have those CAD files. So I'll go ahead and get maybe a alloy steel socket head screw here. And I'm going to go to the left-hand side and start narrowing down my search. I wanted the 3/8 and 16 thread one, as well as maybe I'll choose a 1-inch length socket head screw. And lastly, a black oxide finish. And it narrowed it down to this one item here. And like I said, there were thousands of different hardware, and a lot of them have CAD files associated with them. If you want to know if yours has a CAD file associated with it, you can just look here to the crosshairs, this green symbol there. It says CAD. That means this one does. So we can go ahead and hit product detail, and we can scroll down here to the bottom and see that there is indeed a CAD file we can save. And we can save it as these various different file formats. We'll go ahead and save it as a step file.
Yep, and this is useful, right? If you can't find something in the existing Content Center library, I know. Well, we all know, right? Inventor's got its own Content Center library with a lot of these fasteners in it as well. If some of those don't meet your specifications for some reason, or you actually want to download the actual purchased part, just because it's got a CAD file associated with it, go ahead and add some of these commonly used ones to your custom Content Center libraries, and that'll be really useful.
Right.
So
I'm going to go ahead and move this to my desktop just so you guys can see it a little bit better. I already had one earlier. Let's just go ahead and replace that. Now, if we go back to Inventor, we can go ahead and first, let me get out of the modeling of that. We can go ahead and import that or place that in here. And we'll bring it in as a solid.
Yep, and that dialog box is really important. I know Brian went through it really quickly. There's a lot of options in there in regards to importing non-native CAD file types. Mm-hmm. Really, really important, especially with like the AnyCAD technology. One of those options will let you keep associativity, one will not. And then if you're bringing in assemblies too, there's that second tab there that's really important. If you need to go through that, need to understand how to bring non-native CAD files into Inventor, let us know. We can walk through that process with you. It's pretty simple. There's a lot of options. So yeah, just
sorry about that, guys. Yeah, I provided our email addresses at the end, so we'll go ahead. You can reach out to us with regards to those questions in case I miss anything here. So before I place it in, it gives us a little preview of what's going to look like. What I like to do is right click and rotate it 90 degrees first, a little tip there, and then I'm going to place it in. So now we have our bolt ready to put into the female portion here. But before I do that, I do want to talk about the Excel version. So if you have your own custom threads from your company that you want to maybe show in your CAD file, let's go ahead and go back here to our threads here. So if you have your own custom thread type, for example, what you can do to insert that is if you go to your Windows search and you type in thread.xls, it'll be the one that's lowercase. And this pulls up a file that was downloaded when you downloaded Inventor. And this is why you need Excel when you download Inventor as well, is so that you could reference this sheet here. And this has all of those thread types that we saw in that thread window.
Yep.
And you can edit them, whether it be the name or the major diameter type. And there's a particular formality that goes along with this, and I have that document as well that I will post in the chat room at the end.
Yeah, so like keep in mind that a lot of the Inventor stuff, when you're going through all of these options, it's all referencing like things like Excel tables on the other end for things like some of the sheet metal rules for this, for some of the Content Center, actually not some, a lot of the Content Center stuff, threads, so on and so forth. There's all of these tables, right? And they're just in the application, not application options, but like they're in the application files for Inventor. And this is why sometimes you get that error message when you install Inventor, or you have like you get issues doing this if you have like a unsupported version of Excel. That happens sometimes. So just FYI, if you can't get to this, like we said earlier, let us know. There's a couple of gotchas.
Yep. Let's go back here to Inventor. Let's go ahead and suppress that again. All right, so back to our thread fitting. So now we're going to test to see, hey, does this thread fit with the thread that we created through Cool Orange? So we'll go ahead and do a constrain that cylindrical face with this one here. Now we can see if we move it up and down, it's pretty much locked in. So now I'm going to do a section view. to see how these threads line up. And it looks like they're really snug fit. Might be good for the model itself, but definitely not good for 3D printing, because being that fit, you're going to have to put a lot of pressure and break some threads when you're tightening this bolt or the screw. So what I like to do, and this is through experience, is I like to directly edit the thread itself. This does change the CAD model, but this is specifically for 3D printing. And what I'm going to do is give it a tolerance in between here and here. Give it a little gap so it has some breathing room when you tighten it in. Because the 3D printer isn't perfect. It's not going to print the perfect size thread. There's going to be some offs here and there, and that's why we're going to give it that tolerance. So what I'm going to do is give the tolerance to this bolt, actually, because we can have a lot of different holes in our model, but the bolts or the screw is usually the same. So I'm going to change that one here. So let's go back to the regular view and we'll edit the screw. And if you guys have ever used the direct tool before, this is what we're going to use in this case. And this directly edits the model itself without having to use any sketches or anything like that. And I'll go ahead and select 1, 2, 3, 4, all those faces there. Maybe this one at the bottom as well. And you can do 5 different things. You can move the faces. You can change the size of them. You can change the scale. You can rotate them or even delete them. In this case, we won't change the scale because that might not make it fit anymore, but we're going to change the size of the thread. And I found the magic number to be 5/1000ths of an inch. So I'll go ahead and move that 5/1000ths of an inch in more. And then let's go ahead and see the threads of this model here. And it looks like it's pretty good to go, except right there, there's a little bit of a intersection. So I can go back to the model again, use the direct tool again, and just select this face instead. So this face, I'll move maybe another 5/1000ths of an inch. While the other one, so this one was moved maybe 10/1000ths of an inch, and the rest were moved 5/1000ths of an inch. And play around with it. It could be up to your printer. Maybe it's a really high quality printer. Maybe you can get away with a lower tolerance there. But for me, 5/1000ths of an inch seemed to work pretty well. All right. So now that we have that created and I printed out and it worked pretty well, let's talk about another scenario. Let's talk about if you have maybe this brick here and another brick below it. How do you go about creating a thread that goes through both of them continuously? So I have that example for you guys right here. And what I mean by continuously is that, unfortunately, the Cool Orange tool only allows you to select one face at a time when you create the threads. So if you select this face first, create the threads, then you select this face and create the threads, they probably won't line up the way you wanted it to. However, I'll show you guys a workaround that I found that you can use to have the threads become completely continuous from part 1 to part 2. So we're going to use what is called a Boolean operation, and we're going to bring that screw back in, and we're going to use that to subtract material from our 2 boxes here. So I'm going to go back to assemble, place that screw back in. Constrain it about that face there. And we're also going to constrain it, this face with the top of the box here. Because we want this, when we screw this in, to be snug fit against this surface there. So after we have that in position, we can go ahead and use our Boolean operation. So first I'll go ahead and edit our top part. And we do want to use this screw as our subtracting tool. So we're going to want to copy that object. It's located under modify into this environment as a solid. So now we have this tool to work with and this part to subtract from. So I'll go use now the combine tool. And this is my base body. This is the tool I want to use to cut with. And I want this, instead of a join operation, to be a cut operation. And then it cut threads for me right there. So we'll go ahead and do that. Oh, but also notice how there's this error here. This is because I got rid of that constraint by creating those threads. But that's okay. I'll go ahead and accept that because this is already in position the way I wanted it to be. So we don't need this mate anymore. So now we're going to do the same Boolean operation for the bottom part. So once again, we'll go to copy this object into the model.
Yep, and this Boolean operation is just not useful just for things like this, where he's just adding these threads. The Boolean operation is super useful for a lot of other things. I know a lot of customers who use certain objects as reference into other ones, right? Maybe you have a specific kind of cut, or you need a cut based on the shape of another solid. This is how you do that, right? I get a lot of questions like, hey, I want to cut this slot exactly as this other part is built. How do I do that without, reverse modeling this thing? And generally these Boolean operations are what you want to be doing.
Mm-hmm. And once you get that Boolean operation, notice how it didn't give me like that offset, that tolerance that I'm looking for, but it did give us once again a snug fit to the body. So we're going to use the 5/1000ths rule again. I guess I just made it a rule.
Yeah, the rule of Brian. We'll just call it that.
Yeah. So let's go ahead and instead of editing the screw this time, I'm going to edit our top and bottom parts. 1, 2, select the 4 faces there. Change the size. Use the 5/1000ths of an inch to make it just 5/1000ths of an inch bigger. Good with that. We'll edit the bottom. Direct. 1, 2, 3, and 4 faces. Change the size. And now we have, hopefully, the threaded holes using the Boolean operation. So it looks very similar to the other one that we worked on as well, and it worked pretty much the same when I printed it out. It's also flush to the top because I didn't change the face there. Also, if you guys want to try measuring this to see what tolerance you're getting, I don't necessarily recommend doing it while it's in the section view because it looks a little messy, but you do get your minimum distance here. It's a little harder to read. So what I like to do instead is I like to actually manually cut it. So let's go ahead and turn this back to the end section view, and I'm going to cut it with this rectangle. Just draw a big rectangle. I'll choose the starting point of my rectangle. And then I'm going to cut down, and then we can see pretty much the same half section view, except now we can measure from point to point. So we can measure from here to maybe there, I guess, for example, and it's about 5/1000ths of an inch. We can try again from here to there, another 5/1000ths of an inch. So you can see pretty much like how much tolerance you're getting via this method. All right. So now that we have this modeled and ready to 3D print, we can go ahead and export this as an STL to our slicer. So let's go back to the presentation and talk a little bit about that. So the printers I use for this experiment is the MakerBot Replicator Plus, as well as the FlashForge Finder, and they each have their own slicers with them. And for those of you who are new to 3D printing or are not familiar with the workflow, first you would start off like in Inventor or Fusion, for example, with a CAD file that you modeled up. And then you would export that as an STL to your preprocessor or your slicer. And for MakerBot, for example, has a MakerBot print slicer. It's a free software. There's a lot of free softwares out there that usually come with the 3D printer. Cure is a popular one. FlashForge, Flash Print, I believe the name was, is for the FlashForge Finder one, and those are all free, and they all have the same idea where in the slicer you can create support structures for your models. If it needs support structures, you can create rafts so it could better be stuck to the bed, or you can, and it creates G-code eventually to send to your 3D printer. And that's how that process works. The first tip I have for you guys for 3D printing threads is that larger printed threads are usually more successful than smaller ones. And this is because of the discrepancies that occur from 3D printing. And I'm not saying that all 3D printers have discrepancies, but I'm saying most of them do have like a little bit of a error here and there. If you see in this picture here, there's a line that kind of goes through up and down my screw here. That's due to the transition from it going from layer to layer, and it happens to be at the same spot every time. And that discrepancy is okay in these larger prints, but in the smaller prints, it actually plays a bigger part because the tolerance can be just so. The print size of the extruder or of the plastic has a particular diameter, and the smaller and smaller you get, the more that comes into play. And the bigger you print, the more forgiving that is. And if you have a choppy print that you don't necessarily want to reprint, just because it's a little webby, I would say, here and there, try cleaning it up with a metal nut or bolt. Try screwing it into a metal one, because the metal one pretty much is works kind of like a knife that just like cleans it up a little bit. So if you guys are having a little bit of a issue there, try cleaning it up with that. Vertically printed threads are better than horizontally printed. So if you look at the bottom left-hand corner of the screen, those two are in position for trouble. They're horizontally oriented in the slicer, and they would need supports. And if you print them out, if you look at the top left-hand corner, the left piece, you can see that there's a little bit of overhang, and that thread actually did not come out good. But if you print it vertically, like the one in the picture on the right, or the bottom left-hand corner, the two items on the right, those were printed vertically. They did not need any support structures, and they came out really good. And you don't need any supports usually for threads. Some of them do, but usually all the threads I printed never needed support. So
yeah, it depends on how big you get, right? If you get like super big, then maybe you will.
Yeah.
The other thing too is do bolt head down. Generally, you want to have the end of the thread being upwards, because then you would need like support material on the bolt heads and stuff, and that is not fun either.
Yeah.
So just use common sense.
Yeah, essentially. Third tip: print bolts at 100% density, please. So I tried this one at 15%. I already knew it was going to mess up, but I needed to show you guys that, hey, if it's hollow on the inside and you add a little bit more torque than it can handle, then it'll snap off. All the bolts that I print at 100% density are actually still intact. I applied a ton of torque to it, and it's still they still haven't broken. So that's a good tip. Slicer settings. So people will wonder, hey, what settings should I put my printer at? Usually I left it at the default. Besides the fact that I changed the density of it, other than that, The temperature remains the same. You might have to toggle the temperature depending on maybe the type of filament you have. But for the most part, if you have a good setting for your printer, just leave it at that. The only thing I would recommend is if your slicer has a hyper speed or hyper mode, that allows you to print at a slower speed. And that actually, I compared and contrasted the two, and that gave me a much better print than the regular speed printer. So I would play around with changing the speeds of your prints as well. Maybe from, if you look at the top one, 60 millimeters per second, maybe change that to like 50 millimeters per second. And it gives you that cleaner print because it takes its time as it goes over each layer. So once again, if you guys have any questions regarding your printer settings, if you're troubleshooting that, I would love to talk to you guys about that. I like 3D printing. And yeah, here are our email addresses. Please reach out to us, write it down. I'd love to talk to you guys about the threads in Inventor, as well as the 3D printing slicers as well.
Yeah, Brian's like the in-house 3D printing dude. So if any of us want like to build anything, for example, we just like go to Brian's desk. We're like, hey, can you print this? The printer is actually like upstairs in our office here. If you've ever been to the KETIV offices, we have a downstairs and an upstairs training room. The training room is where the 3D printer is housed, and it's not uncommon that we see Brian up here just like messing with the thing or like pulling something really random out of the 3D printer. So it's actually really fun. All right, with that, let's go ahead and get to a couple of questions, make sure that we can go ahead and address these for everybody. First question, I'll go ahead and address. Can you edit the threads with the offset function in Inventor as well as like the direct edit move functionality? Did you ever try that?
The threads with the offset function.
Yeah, when you created the tolerance between the bolt and the nut, did you only use the direct edit functionality, or have you tried using the offset functionality?
No, I've only used the direct edit technique, but the offset function seems like I would have to try it out.
Yeah, I'd have to try it out
Yeah.
too and see if it works, because what'll happen probably, I have a feeling that when you do the offset functionality, because the faces are separate faces, you might get into issues where things are like, you're going to get an error. I have a feeling this is what can happen. You're going to get an error that says the faces are like colliding with each other.
Yeah.
And then it doesn't know what to do.
And there's a bunch of different ways you can create these threads. These are just some of the ways I wanted to share with you guys. There's multiple different ways. And also, just to mention, this is the disclaimer as well, maybe the thread, the direct editing, like it wasn't perfect every time in terms of it. Sometimes it gave me an error for the same reasons Nigel just said. The offsetting might have been interfering with each other, and
yeah, the faces will like collide and stuff, and then sometimes you'll like do one of those direct edits and then it randomly turns into a surface and you're like, what happened here?
Yeah, so you have to just find the best method. I like using the direct edit feature because it's really straightforward, it's really simple. But if that doesn't work, I might try maybe the offset, or I might try the Boolean operation or something like that.
There's a lot of ways you can do it, so go ahead and play around with it. And like we mentioned earlier, don't do this for like your 500 part assemblies, please. Break that down into a sub-assembly if you want to make sure that a couple things fit together, and do it that way. If maybe for example, you don't want to order like 25 of a certain bolt because you don't know if you want to use that one or another one. This is one of those use cases where it's like, okay, like, does this work in my assembly versus the 2-inch bolt instead of like the 1-inch length? This is like a really good use case. Yeah. For those situations, because you don't want to necessarily be buying boxes upon boxes upon boxes of bolts that happen to be the wrong size.
Definitely consider printing your bolts before buying, like Nigel said, boxes of it. It helps to test it with.
Yeah. Also, like double check when you're ordering these bolts too. I have a funny story. As I have a customer, I'm not going to disclose who this person is or who that company is, but while I'm telling the story, Brian, if you want to grab the links and put them in the thing.
Yeah, sure.
They manually entered all of their purchasing, and they went to go order some fasteners for their assemblies. Wanted to order 10,000 fasteners. Human error added an extra 0 to the end of that. And they ended up ordering 100,000 fasteners. Not the greatest thing in the world.
So that first link that I posted for you guys is for the Cool Orange add-in.
Brian, you only sent it to me.
Oh.
Make sure you send it to the whole audience. Go ahead and click this button. Yeah. Okay. Only I can do it, huh? Okay, I'll copy and paste it. No worries, Brian. I'll save you.
Nigel.
I will save you.
And so the first one will be the Cool Orange link to download, and make sure you sign in for that. And then the second one is going to be, what is that second one?
The second one's the thread data spreadsheet, if I remember correctly.
Right. Oh yeah, it's the formalities for the Excel sheet. If you have your own custom threads or values that your company has, then take a look. Definitely take a look at that.
Yep, definitely. Yeah, go ahead and like download, start using some of those tools. It is not the most frequent thing in the world to be able to have to model threads, especially if you're like building industrial machinery. You definitely don't want to do it because in your top level assemblies, that is, because then your files get super, super heavy and they take forever to open and so on and so forth. So definitely keep that in mind. That's how the Content Center stuff in Inventor is built. It doesn't have the threads on it. It just has the visualization of those things. So keep that in mind. It's just useful for, having placeholders for stuff, so on and so forth. But if you need to actually test the fit between two objects, or do like some of the continuous threading stuff that Brian did, for example, you can do that. And if you have a really, really cool like sintering printer, and you can like make metal versions of all of this stuff with the threads, I'm jealous because I want a laser sintering machine so we can like do metal stuff. Yeah, so let's keep going here. Alex definitely mentioned too. Another good use for the Boolean operation is to build things like soft jaws. If you are machining objects, to build some of those custom soft jaws to be able to hold your stock.
For those of you machinists out there using
Exactly.
CAD,
yeah, super, super useful, and that's a workflow that's pretty popular among those people. Let's see. Yeah, definitely, Daniel. Agreed too. It's like printing threads at 45-degree angle seems to work pretty good too.
Okay.
Yeah. I'll make Brian try that. Brian, that's your new thing, is to start printing these threads sideways and see what's going on.
Sounds like fun.
I think you're probably going to be able to apply more of a torque to them before they break, especially if you don't do 100%. Just based on how they're built. So.
And for that, it looks like I would try also, if you want to create your own custom threads, try using a coil and a profile and sweep that around, and then you can create your own custom threads, and then we can angle that at whatever angle you want.
Okay. The slope of the thread face is 45, not the print.
Oh.
I mean, I still want to do it. So could you please print a bolt for me at 45 degrees?
You thought it was.
Yeah,
you thought it was
really confused.
The orientation.
Yeah.
Of the slicer. No.
Yeah,
I was on the same page with the.
That's funny.
Yeah.
Yeah, I was on a different page, and I'm like, dude, let's print these things sideways. It sounds great. I'm gonna try some weird stuff later. Anyways, I think that's just about all of them. There's another question. How do you know which faces to select when direct editing? Select all faces on thread.
No, not true. Not true. So that's what you have to play around with. For the example that you guys saw, when I did the selecting for the direct editing, I selected all of them. But then the second time around, I selected just one face because that's the only one that was interfering. But you do have to play around because not all threads are the same, like the one you saw here. Sometimes it doesn't even work, the direct edit.
Sometimes it's not a
method.
continuous face.
So keep that in mind. Yeah, and you might need to use maybe a Boolean operation instead. So it's definitely a trial and error. But if you have the same common thread that I chose today, then you can select those faces there. It's not necessarily all the threads every time.
And you'll get occasionally, like I said, error messages talking about like colliding faces, or like I can't cut through this face that's also cutting through myself things. So being able to interpret those error messages is a really big thing. And the easiest way to do that is to copy that error message, paste it in my good friend Google.com, and search. And that's generally like if you get run into anything weird in Inventor, odds are that someone else has run into that issue as well. And there's like a really big community of people online, generally the Knowledge Network or the Autodesk forums, where people have given a lot of answers to some of these common error messages that might not be the most intuitive when you read them for the first time. So just keep that in mind. I think that's just about everything that we had for today. Everyone else who's involved in AVA, thank you all for being, part of this whole process. It is the help of all of us that gets all of these things done every week. So again, thanks everybody for joining us, and we'll see you next week. Same time, same place. Autodesk Virtual Academy.